my office. I'll tell you what, why don't I get these back on Monday? All right, can you just send me an email? I'll make sure.
Yeah.
All right. What's funny is when kids come back, he didn't look much different, but now he's got a wife and 2 kids walking with him. I feel you should know their name, but at least I don't. Okay, so I gave you some homework, and I got at least one question. Jacob, you sent me one on did you understand that? I'm going to go through this. This is all about Bode plotting stuff, but 2, 4, 6, we're missing. So, well, I guess just after test that happens.
No.
I didn't get the scale on this exam either. Let me send that to me in the note too, to send out the scale. Okay, that's my bad. Okay, so first I want to go through Bode plotting in general applied to electrical and computer engineering. Then I'm going to talk about a couple of the problems. And you know, the Bode plots are the way to really go about analyzing the behavior of these components and figuring out where the resonant frequency is and things like this. Because usually, if you look at a plot, you can kind of approximate it. So anyway, when we talk about Bode plots in general, now you've had this, at least you should have been exposed to this in signals and systems in your circuit courses and probably your microelectronics courses. Usually this is, you're going to see it 2 or 3 times by the time you get D negative. So what is it and why do we do it? Well, we do it because it's an approximation of the actual behavior of something, but it gives us a real easy method of figuring out where the poles and zeros are. So when you have a function in general, and it doesn't matter what this is, I'll call it an impedance of S. And remember, S is usually given it as J plus J omega. And when we talk about just the frequency domain, we set sigma to 0. That's just standard. But Z is a function of this frequency S. Usually it has some constant K. As a matter of fact, it always has this. This is just something that scales things. Then it has things that are zeros. It means when S equals a certain value, it will go to 0. And it will be S plus, call it A, S plus B. Here, when S is equal to minus A, that would be a pole. When S is equal to minus B, it would be, I'm sorry, a 0. It sends the function to a value of 0. And if I divide it over S plus C, S plus D, and this can go on and on. I mean, you can have as many poles and as many zeros as you want. I don't prefer to talk about an infinite number. I like to just talk about a finite number and talk about what goes on. Now that in itself, if it's an impedance, is in ohms. But the way we usually talk about these things, we talk about it in terms of a Bode plot, or what we'll do is take 20, we'll call this Z and dB, we'll take 20 times the log of the magnitude of Z. And in our case, that's 20 times the log of the magnitude of K, S plus A, S plus B, over S plus C, S plus D. I'm just showing you the way it's usually done. Nothing more than just sticking in the value of Z I've created down here as an example. And then you have to be aware of this. Now, I always say these things, not to insult you, but just to remind you, because I'm suspect of forgetting things that are simple too. If you have the log of A times B, that's log of A plus log of B. Everybody follow me on that? Nothing fancy here. If I have the log of A over B, that's log of A minus log of B. Are you with me? Again, just so everybody's on the same page as this. Then, if you have the log of, say, a to the n, that's actually equal to n log of a. These are things that I'm saying for a reason that'll be apparent in a second. You all with me in this class?
Mhm.
All right, so when we talk about this, I'm going to go ahead and I'm going to break up this function. I'll leave the 20 out here. And then I'm going to say it's 20 times log of k, right there, plus log of s plus a, plus log of s plus b, and then it's going to be minus log of s plus c minus log of s plus d. And I hope you can all see that. Again, stuck in the values, and I apply that operation and that operation. Okay. Now I'm doing it for a reason. When we actually look at one of these, say 20 times the log of s plus a, just by itself for a second, consider this like a sidebar. 20 times the log of s, magnitude of s plus a, that's actually equal to 20 times the log, if you get specific about being in the frequency domain, of the quantity square root of omega squared plus a squared. You all follow me on that? Here I've replaced s with j omega, and I'm getting the magnitude. So you square the omega and square a. With me?
Mm-hmm.
Now, what normally, you can do it this way. I'll show you the normal way of doing things. You may see something like this in a book, and they're going to say that the value of this when omega is much, much smaller than a is just 20 log of a. That's one thing to do. What I like to do, and this is the way I think it's taught in your signals and systems course, is I'll start here and I'll divide everything by that a. So I'll have 20 times the log, and then since I'm going to be dividing by 8, I'll have the log of quantity a times s over a plus 1. Y'all follow me?
Mm-hmm.
All right, now I'm doing it for a reason. I'm going to break that out to two functions. So now I have 20 log of a plus 20 log of, and this would be s over a plus 1. Unless I change my phone number. I don't know if you realize that. Before I get done, I got to tell you something. So my wife had an area code that was not here. And she changed, she got a new number when she got a new phone. And it is a 334 area code. However, the thing they don't give you is a brand new number to find it. So the person that had this before is named Herschel. She's got all these messages all the time. Herschel, man, get back to your mom and stuff. I mean, just one after another. I'm not kidding about this either. And she's like, can I get another phone number? I'm not. Has anybody else got a phone number ever, a new phone number that somebody else had used? That's never happened to me. I've kept my phone number since the beginning of time, it seems like. And I still get a lot of crap, but I don't have people call me Herschel. All right, so we're down to here, all right? Now here's the real reason. Just take a look at this for a second. You can think of this as just anything. The 20 log a is a constant. Do you agree with that? We don't know what the constant is. A constant. When I look at this, if I think about what I just did up here, I know I substitute, if I would really want to do a plot of this versus omega, I'll substitute in S is equal to J omega, right? And since I want the magnitude, maybe I didn't put down magnitude. This should be magnitude always in here. The magnitude of that, I have to take the omega over A and square it plus 1, right? Y'all with me? Now here's the real reason I'm doing this. I'm going to do it right under here and then I'll erase. So I have 20, I'll call this a function, just call it F. Now I'll call it S equals J omega. And that's going to be 20 log of A plus 20 times the log of the square root of omega over A squared plus 1. With me? Okay, now I'm going to plot it the way I told you before, and this is done all the time. On this axis, we're going to plot the log of F, or log of omega, because I've got omega there. And I'll call that 1, 10, 100, 1,000, and so forth. With a logarithmic plot, each increment is going to be a logarithmic larger value than the prior. A scale of 10. I should say 10 right here. Now on this axis, what I'm going to do is plot this function, and this is in dB already. I've got 20 times the log of that. So when I plot it, it starts out with this value at very low frequencies, and it has 20 times log of A here. Now, if you look at this at omega, say omega over A, much, much less than 1. You all with me on this? So omega is much less than A. Really, we're talking about the log 1 here, aren't we? What is the log of 1, people? 0, right? So there is no value to this until you hit the value omega equal A, wherever it is. If this is A here, then when you hit omega equal A, this would be a straight line. When you hit omega over A, now you get 1 squared plus 1 squared, right? Or the square root of 2. Do you follow me on this? Now just listen to me carefully on this. 20 times the log of the square root of 2. The square root is really 1/2, right? You can take the 1/2 in front. It's 10 times the log of omega squared, or really of 1 plus 1, or log of 2. Well, 10 times log of 2 is 3 dB. Y'all follow me? It would be 3. That, you've heard the term 3 dB point over and over, I'll say. That's the point where all of a sudden a single pole or a single zero becomes the dominating factor. Beyond that point, y'all follow me? So really, in truth, we approximate these. If this is A here, we just draw a straight line to that, then we start going down. And notice this right here. For omega greater than A, a lot greater than A, then this is really just 20 times the log of omega squared over A square root, or really just omega over A. You all follow me? Now, that means anytime omega, if you look at omega over A, just think about what I'm saying. If I have 20 times the log, and here we're going to assume omega is much greater, or is much greater than A. When I have 20 times the log of omega over A, just think about this. If this value is 10, you get a certain value, right? If it was 10, the log of 10 is 1, it would be 20, correct? Now, if it's 100, it's really what? 1 decade, right? A decade is a factor of 10. If this becomes 100, well, the log of 102, then it would be 40, right? Mm-hmm. If it would be 60, then, if this would be 1,000, the log of 1,000 is 3, then it would be 60. Or the rate of change is 20 dB per decade, and it's increasing. So actually, I've got it decreasing here, but technically this one, because it's a zero, it's going like this. Now it starts going up at plus 20 dB per decade. Usually you'll just see a plus 20. If you're getting correspondence from people and doing engineering, you'll just see plus 20. It's implied dB per decade. and that's going up. So that's what this would look like, the Bode plot of that. But remember, there's two ways to doing this. You can come up with this part. Y'all see this? Then you can say as omega is very small, you get 20 times the log of, well, it's just square root of a squared, which is a, so 20 times the log of a. Same thing as I got here. Y'all follow me? And where all of a sudden that changes is when omega equals a, then it starts going up by 20 dB per decade. Now the real truth is if you look at an exact plot of this, you'll see this. Like this, and this will be a 3 dB difference between the actual value that you have and the approximate value. We always use straight line approximations in engineering to show this, so it's real clear. With me? And now we're going to plot that thing, and then we're going to do the problem I gave you. And I'm doing it just so everybody has seen this, and I know for sure you haven't got some bizarre explanation, because there are some people that do this kind of in a convoluted way. And since we're going to use this a lot, I want to make absolutely sure about this. Did you all get this in circuits or not? Bode plot?
Not in circuits, but in signals.
Yeah, who did you have for signals?
Oh, man, what did you guys name? Dr. Son?
Okay, I mean, you had it here then.
Yeah.
Okay. Do y'all have it here? I had, he's not here, but one other guy. All right, I want to tell you one thing. It's so important to understand this. A lot of people don't really understand this at this level. And I hate to say this, that's the reason I'm spending so much time. And if you've done labs where you've had these plots, right? Mm-hmm. Well, I'm glad I'm not grading lab reports, because I know that kids can vouch these like crazy. Now, I don't need to put everything in terms of J omega, all right? But I do need to divide out the constants. With me? Mm-hmm. So what I'm going to do is say, even though you're going to see that sometimes, I'm going to go and I'm going to divide out all the constants first. Now, in the first one, I know, I'll tell you what, we'll do it right from the top. So you see it. If I have this, really what I want to do is take 20, right, times the log and magnitude. I'm going to put K by itself right here. Now look, I have an S. I want an S over A, right? So I factor out an A and divide by an A. Right? Now I have S over A plus 1, correct? Y'all with me? Now the next one I factor out a B, right? So then I have B times S over B plus 1. Downstairs, I factor out a C, and I have S over C plus 1. And then I factor out a D, and I have S over D plus 1. And I do that because I like getting all the constants as just one package term. I don't like having to evaluate each one of those terms when it turns on. So now I have that as such. And now I'm going to get all the constants out to one thing. So I have 20 times the log of magnitude. Now it's K A B divided by C D, right? That would be one constant. It would be the log, right? And then I have the rest of these things. Then I have plus 20 times the log here, S over A plus 1 plus 20 times the log of S over B plus 1 minus 20 times the log of S over C plus 1 minus 20 times the log of S over D plus 1. And I know these logs, I didn't put them here. These are all magnitudes. Has to be. So that's the plot. I mean, that's what I want to plot, and that's Z and dB. And now I'm going to do it here. but I've got to make some statements about the values of A, B, C, and D's relative strength. So I'm going to assume A is less than B is less than C is less than D. I've got to choose something where I can't plot it. I mean, we can mix it up if you want to go the other way, it's fine too, but I have to know where these are. So when I'm plotting on this axis, it's the log of F, or omega actually, let me do omega. Right? And we know S is equal to J omega. And on this axis, it's going to be 20 times the log of magnitude of Z. Agreed? Now, the way you always do these things is you assume omega is 0. Now, sometimes you can't do that because you got a 1 over 0. You got it's called a pole. It's coming in at that value. So you just approximate the line coming in. And there has to be some value at some value of omega given in order to do this stuff. If not, well, I can show you how to deal with these things, but normally they give you some point. So what I take a look at, when S goes to 0, all these are off. They're all log of 1. Right? This is the only thing. So that's the entry point. And I have right here, this is 20 times the log of the magnitude of KAB over CD, whatever it is. And now I've got A is first, so here's A, here's B, here's C, and here's B. I come in, it's flat, and the first thing I hit is going to be a 0, so it starts increasing at 20 dB per decade right here. Y'all see that? So actually, let me do it down here. I'm going to say this is my point of entry. Then from here to here, I'm going up at a rate of plus 20 dB per decade. I don't know how far I've gone up. I'm going to show you how you calculate that in a second. I just know that's the slope of that line. You with me? Because I didn't give you a relative value in A and B. Then at B, now listen carefully to this. At B, all of a sudden, this one turns on, right? Correct? So now it's going to not go up at 20 dB per decade, but 20 dB plus 20 or 40 dB per decade. This is important to see this. So now it's going to start going up at 40 dB per decade. With me? Now you keep going, and I hit C. I mean, the magnitude of omega is C. With me? This one turns on. Now it subtracts 20 dB per decade from the 40, or it goes back down 20. Okay? And it's doing that, right? Then the final part, when it hits D, and this isn't exactly drawn a scale, but if that is D here, then it just flattens out. That's it. And that's how you plot all these things with Bode plots, no matter what. And you can extrapolate. If you have a plot of something, you can extrapolate the values for the break frequencies or element values. The very first problem that I think I gave you that didn't have the entire solution showed you something where they used P for instead of S. Many, many times in the real world, they'll pick an arbitrary symbol, maybe a Greek letter, could be gamma or whatever, to be designated as the variable S. And it doesn't matter what it is. And then they want an approximate function. Just remember, all these things have to have either F or omega in them to do a Bode plot that's got any meaning. All right. Now that I did that, now we're going to talk about, well, how would you figure what the actual value was here, or here if I give you some specifics. With me? This is important. It's not covered in your, well, maybe it is covered. I think I cover it when I teach signals and systems, but I don't know if everybody does. So I'm going to leave this up right here, and I'm going to change. I'm going to give you some exact values. That way we can do this exactly. So I'm going to say A is equal to 100. B is equal to 525. C, actually, let me do it this way. C is equal to 525. I'm going to go D is equal to 2,000. And then B is equal to 3,000. Now these are arbitrary. So now I'm plotting on the horizontal, and I want to plot this function. Well, let me do one other thing. Let's just make K 1, make life easy. Well, what I want to do is plot, let me do it at this corner of the board. I want to plot versus log of omega, the value of this. So it's in dB, I got the 20 ahead of it. So if I look down here, I know for a very low, first the lowest frequency is A, so I put A down here. Now really A is 100, right? Mm-hmm. But if I take the log of that, then that value would be 2, right? So scale-wise, it's 2. Y'all with me on this? Because we're plotting the log of F, or log of omega, pardon me, omega. So that's, and I better just put 2, not that. That's 2. The next frequency I hit is C, and it's 525. Let's see. Log of 1,000 is 3, log of 100 is 2. What is that, 2.7 something? I'm just trying to estimate it in my mind. 2.78, 76? Or am I way off? Log of 525.
2.72.
All right, 2.72. All right, and this is really 525, right? And this is C. All right, get rid of that. You know, the next value, I'm trying to show you relative. These are fairly close. That's what I'm getting at. Right. The next one is 2,000. So a log of 1,000 would be 3. Log of 2,000 is 3.2. Is that it?
3.3.
3.3. So we got 1,000 up here. Or 2,000, pardon, 2,000. And that's D. And the real value is 3.2.
3.3.
3, pardon, 3.3. Be nice if I had graph paper. Then, finally, 3,000, which is about here. And 3,000 has a log of
3.48.
very close. But you can see all this stuff's chopped together. Even though we went from 100 to 3,000, there's not a big spread in the actual plotted point. Y'all with me? I'm just trying to show you because it's a linear scale. Now, I start by coming in right here at the value right here. Log of A times B, so it's A times B. That's 10 squared times 3 times 10 10 cubed. So it's going to be 3 times 10 to the 5th, right? Divided by, or sorry, yeah, that's right. No, 3, that's, when I put these numbers in there, I got 100 times 3,000 divided by 2,000 and divided by 525. So it's really 100 times 3 divided by 2 divided by 525 and times 20. So can you tell me what this is, just so we have something down? K is 1.
So the log of all that is negative 0.896.
And then multiplied by 20.
20, we're looking at negative 17.93.
All right. Minus 17.93 dB. That's where our starting point is. Now we keep going, and the first thing we hit is A, and A is going to be a 0, so it's going to start increasing, right? Now just listen. We know what the value is right here. It's going to increase all the way up to 525. Just watch me. We'll get the values in a second. Goes up to 5. Hold it. Yeah. Well, that'll have to do. So when we hit 525, that's C, and C is a 0, right? Or I mean a pole, right? So now it's going to start going down by 20 dB, which means it flattens out, does it?
Mm-hmm.
Then I hit 2,000. And 2,000 is another pole, right? The D value. And that means it's going to start going down to 20 dB. And then when I hit 3,000, it levels out, correct?
Mm-hmm.
So here's the kind of question you can get from it. Based on your knowledge of this, you've got that point. What does this point level out at? Now, some of you are thinking, well, I'll just take the darn equation. I mean, you could take this equation right here, and you can simply, or basically take this equation, and if you look at it carefully, as S gets very large, what happens? I have S squared on top, S squared at the bottom. It goes away, doesn't it? You all follow me? It cancels. So for very large values, it'll just be 20 times log K. Does that make sense to everybody?
Hmm.
And what is the log of K? Log of
0.
I'm sorry. No, it would be the log of 1, right?
Mm-hmm.
Log of 1 is 0, so you're right. It is 0. Anyway, you can see that. But here's how you get like this point right here. And it's important you listen to me. That frequency, I'm just going to call it omega A. All right? This frequency I'll call omega C right here. And I want to figure out what this value is, all right? Now, please just listen. So I know I've got minus 17.93 dB I start at, and I got to figure out where I finish. So this point right here, and I'll just call this Z of 525 dB. Here's how you get it. Start with the value down here. Minus, please watch this, minus 17.93. Then it's going up to 20 dBs per decade, right? So the next thing you put down is 20 times the log of the ratio of the frequency it ends at divided by the frequency it starts at. Remember, if that ratio is a full decade, or the log of 10 is 1, so you'd add just 20 to that. Follow me on this? But if it's any other thing, it's going to be less than or greater than. So it's really going to be omega C divided by omega A. It's just the ratio of the two frequencies inside the log. Do you follow me? Always take the upper one, subtract from the lower. You got me on this class? So I don't know what that is, but what do you got? It's really the log of 525 over 100, really log of 5.25 times 20. You want to give me that?
Negative 3.53
All right.
dB.
So, and then add that to 17.9.
That's already added. I already did negative 17 when I did the whole equation. So
Okay, what did you get?
it's negative 3.53.
Minus 3.53 dB. So that's this point right here. Put it down. And it stays there, right? Until I hit this point, correct, class? Now, if it started going up at 40 dB per decade, then what I would do is add plus, at this point, I'd have to find what the value is here, all right? And then I'd add to it plus 40 times the log of whatever the frequency was it finished at, divided by the frequency it started. Yeah.
So it's not the cumulative.
Well, it is, but you don't add two 20 dB lines. What you end up doing is, if you know this value here and it starts going up from that point at 40, you know the slope of the line, right? You just go ahead and say it's this value, whatever it is, plus 40 times the log of the difference in frequencies. That's the key to remember. Make sense? Okay, but in this case, it doesn't. It starts going down, right? So if we're here, which is the same point as here, right? I take that value, and now I'm going to subtract off minus 20 times the log of 3,000 over 2,000. So then this is going to be the z of, what you call it, of not 525, but of 2,000, right? No, of 2,000.
3,000.
So this is the z of 2,000. My bad, right?
Yes.
All right, so now we want the z of 3,000. And the way we get that is we take this and then we subtract minus 20 times the log of the upper frequency, which is 3,000 over the lower, which is 2,000 or 3,000. Now what do you get there?
So your final answer is going to be negative 7.05 dB.
This plus this?
Yes. It should be greater in magnitude. It should be a more negative number. Goes down.
Yeah, it's going to be minus, say that again?
Minus 7.05.
So what is the log of 3/2?
Log
It's greater than 0.
is 0.176
Times 20,
times 20 is 3.52.
and that's 3.53. Okay, all right. So that would be the final value, but something's bugging me about this.
I think the scale is off on the thing. It shouldn't be more negative than the starting point. It should, because it travels a much less distance, 3.3 to 3.48 on like a scalar scale versus the 2 to.
Well, when it was going up, see the ratio of these two frequencies tells you how high.
Mhm.
525 divided by 100 is 5.25.
Yep.
That's how much it gained. How much did it lose? 3,000 over 2,000.
It's 2 or just 1.
That's only 1.5.
Yeah.
So it lost a lot less than it.
Hmm.
I mean, in other words, there was a net gain, and that makes sense. But I'm looking at this thing. Hold on. What is this number right here? That's 17, huh?
Yes.
Some are starting to make me suspect, but I'm kind of trusting. I mean, what I'm showing you is how you do it.
Yeah.
I'm looking at that thing.
Because you're getting A times A times B. I'm gonna try
30,000 or
100 times B, which is 3,000,
A
over C times D, which is.
times C, D belong. A, B.
I think that number is off actually, because I think
It is.
I did A times D and over C times B, and not inverted the B and the D around. Hold on.
So that's really gonna be 20 times the log of 8 times B is 3 times 10 to the fifth. Then this is gonna be,
It's negative 10.88. So this one's. Let's get that right.
tell me what that is.
20.
Log of 3 times 10 to the fifth over 2 times 10 to the third times 525.
You're looking at negative 10.88.
Is that what you got for the second one?
That yeah, that's what I corrected it to after I
Minus 10.88?
yeah,
That's,
and that'll just change.
that's,
It'll shift us positive and probably on the.
that's right. I'm sorry I spent so much time on this, but I wanted to show you how to do this, how to adjust the scale.
Mhm.
All right, and that will cut through everything. You can do any problem you want. Now, do you have any questions now based on this of the homework I've done for you?
Could you do, I think this, does anyone have, it was the second Bodie plot one, I didn't really get, I got your email, but I didn't quite understand how to get the kit concept.
You understand what I was going over today?
Yes, sir. I don't know.
It should be a straightforward thing, but let's do it.
Talking about 5.4.
What's that?
I was able to take the impedance expression, I just couldn't figure out how to get the coefficient.
All right, let me do it. Is this a picture problem?
Yes.
All right, help me out. Go ahead.
The magnitude of impedance is sketched at 30 plot figure whenever determining one possible impedance expression.
And just flip it over a second. All right, this is the one that goes up, right? Okay. That right there, it looks like I'm not sure what this is, but it goes up like this, right?
Yep.
Hold on.
At about plus 20 dB per decade, and then it goes down at negative 20 dB
Right.
per decade, starting at omega equals 10.
And then it's flat.
Flattens out at 30.
All right, is this versus omega?
Yes.
All right, and what's the resident frequency here?
10.
10?
Yes, sir.
It starts here at what?
Maybe about 30 dB.
Minus 30 or is it given or not?
It's not given.
And what frequency?
Doesn't say.
Right here.
It doesn't say.
It has to.
Where?
It doesn't look like it does.
Is it given in the?
Yeah, it is, right there. I mean, sorry, where's that 0 dB? Is that up there?
0 dBs at 30.
Okay, that's fine.
Or the 0 dB per decade, but
Is this 30 right here?
yes.
Okay, we got it. Is this look, you know the slope of that? You can put 1 here, and if it's 20 dB per decade, whatever this value is, this is going to be 20 less. And then this value was 0 dB.
The value there is 25 dB.
Oh.
Um,
Just 25?
Yeah.
And anything else with that one?
Z is equal to, Z of P is equal to 18 P.
No, that's the answer.
That's close.
Is it 0?
What?
No, that's the slope.
The slope is 0 dB. It's flat, in other words. All right, this is going to be, in this axis, this is going to be 20 times the log of the magnitude of the impedance. Is this omega or F?
Omega.
Fantastic. Now, we know really that S is equal to sigma plus J omega. Really, we can forget about sigma now. All right, when we're doing this one, it's really putting together poles and zeros. There is nothing that says this pole stops. All right, I'm sorry, this zero stops. This thing's been coming in straight. So normally when we construct this function, we're going to put down Z. Just by looking, I start with a 0, and there is no start point in that, so I just put S here. You see, no matter what, how low you go, if you add an order of magnitude to the frequency, you go up by an order of magnitude. With me on that? In terms of, it would be, that's the linear coefficient you're going to use for this part, just S. Now, I hit a pole at 10, right? So then and by the way, you always put a constant there. So it's K times S. Then I have S plus 10 because of this pole, right? And then when I take a look on here, then there's another 0 right here, correct, class?
Mhm.
I'm sorry, this is minus 20 dB. It was going up at 20, it's going down at 20, so this is actually squared, my bad on that one. Because it's just 20 would flatten it. It has to be 20 plus 10 quantity squared. Follow me? Because now it's going down. Then it flattens out here, and that's a 0. So it's S plus 30 here. And that's Z. Now, before I even take the log, I like to factor out all the constants. So I have S divided by something plus 1. That's just the way I do it. So I'm going to say Z equals K. And then if I look at this, the S can stay by itself. And then I have S plus 30, so I take out a 30, right? And then I have S over 30 plus 1. And it's really times S here, divided by, and then here I've got to take out a 10 twice, or 100, right? And then I have S over 10 plus 1 squared. Agree?
Mhm.
I mean, I'm pulling out the constants. If I pull it out, if I put S times 10, I pull out 1A, then a second A, right? I'm sorry, that's the second value of 10, and I get this square. Then I go ahead and I take 20 times the log of this Z, because this is going to be what I want to plot. And that means I have 20 times log of magnitude, it's really K times 3 over 10. Right? That's this part. And then it's going to be plus 20 times log S over 30 plus 1 plus 20 times log S minus 40 times log this will be magnitudes, of course, S over 10 plus 1 squared. right?
Because you have 40 in front, you still need the square term.
No, you don't. You're absolutely right. I should have just, you're absolutely right. That was my mistake. It should be a magnitude. Okay. Sorry about that. Okay, now when I'm doing this and plotting it, the only thing I really need to do is, I could even do it right here, as S gets very large, I know this is what I'm going to end up with. So if you look at this expression, we can actually do it this way. And I'm sure this agrees with the book right here. If I take and I would go ahead and square this thing out, I'm going to have this be equal to K times the quantity, and then it's going to be S squared plus 30S, right? And then it's going to be S squared plus 20S plus 100. I just went ahead and squared it out, just so you can see. As S gets very large, the S squareds dominate, right? And that means as S gets very large, if I'm plotting this thing, these two cancel, and I get the log of K. So right here, you can put down 25 dB is equal to 20 times log of K. Does everybody follow me what I'm doing?
Yeah.
If you let S get very large, and you know you're going to be out here, and therefore when you take 20 times the log of this, I've got S squared over S squared is just 1, isn't it, class? So this will happen. And if you look at this, that means I have 25 over 20, so I have 10 to the 25 over 20 is equal to K. For the K I've got down there, and what is that value?
17.78.
17.78.
10 raised to 25 over 20.
Hmm?
10 raised to 25 over 20. 17.78. Yep.
Okay. And now he probably gives something that looks like this, right?
Yeah.
And what does he have?
Instead of 17.7, it's just 18, and then the rest.
You rounded. You rounded. Huh?
The rest is the same.
But that's how you do that problem. And I mean, that's it. Then if we could go back and take a look, and that's going to fall, everything's going to agree. All right. All right. Other questions about the homework? Y'all follow me? This isn't that tough. It's just that you have to be attentive. All right. Now, continue on. If you didn't have any more questions about the homework, you can see, like, for resistors and stuff like this, here's something for a typical resistor. I want to just do this one. We could do inductors and we could do capacitors. But the Bode plot of a typical resistor is always nice to see, as well as a capacitor and inductor. But the resistor is the one, if you see this one, the others, you see no problem. For a standard Bode plot of the resistor, you have the resistor R here. We know the high frequency model of that has both capacitance and inductance, right? Usually they do this. They're going to put a resistor here, R. There's going to be some capacitance in parallel with it that's undesirable. And there'll be an inductance that's undesirable that has to do with the leads. And they'll want to know what this thing looks like when you plot it. We can go through the whole 9 yards of this. And if we take the log of S here versus 20 times the log of the actual impedance of that resistor, what we'll get is this. It'll be a constant value, and this will be just 20 times the log of R, whatever the actual resistance is. Then there'll be a point right here, and that will be where really F is equal to 1 over 2 pi RC, or omega, since we're plotting omega, is really 1 over RC. That's the first cut frequency. It's the low frequency. And it'll start going down at a rate of minus 20 dB per decade here until it hits the self-resonance. And this will be just 1 over the square root of LC, and or at F, self-resonance is equal to 1 over 2 pi square root of LXCX. And then after that point, it's going to start going up at plus 20 dB per decade. And that's what a resistor will look like all the time. At very high frequency, the inductance, the lead inductance is the thing that dominates. It'll always look like that for any resistors that are really acting as resistors. And here's the deal, when you have one of these things, you don't want to operate even near this point. You want to be down here by about 30% of this frequency. Y'all follow me on that? And I don't think Dr. Wentworth's book gives you any kind of actual information like a text sheet on resistances. But when you buy them, you'll see one of two things. You may see the resonant frequency and what'll be the bandwidth. If it's the highest frequency that the thing should be used for, no higher. Or they'll give you a spec sheet and they'll show you impedance versus the 20 times log of the impedance versus frequency. Usually they do it that. And you'll see it'll go and then all of a sudden start going down. Whatever that frequency is where it starts really dumping down, you got to work below. That resistor is no good at frequencies approaching that or higher. You don't want to ever do that. With inductors and capacitors, the self-resonance is what you look for. But they'll have that, whatever the self-resonance frequency is for inductors and capacitors, try to work an order of magnitude below that. Don't get anything close to that or else it becomes a problem. And that's just sort of common sense. But that's the one usually that you should understand. And I think you do. So next. I don't know. Did I go? I don't think I went through bandwidth with you, did I? All right. Here's where I have to do a little, because we're going to do the shielding part I've already covered somewhat, right? Remember the shielding? And filters are fairly straightforward, but I'm going to go through this part. I know it's the last 15 minutes of class. Let me just tell you one thing. When I teach EMC or radar, I make sure everybody appreciates and understands the importance of understanding how to go ahead and take a real square wave, which is not a square wave, it really has a rise time and fall time, and analyze it in the spectral domain so that when you actually see, because most of the stuff we have today, let's just be honest, that computer, your phones, they don't have a 60 hertz generator or anything like that. What they have is a square wave generator. It's called a clock. And there's clocks all over, and they usually are between 0 and 5 volts or 0 and 2.8 volts, something like that. But they're binary. They have either no voltage or a positive value on the clock, and that is a thing that runs the JK flip-flops and is used for everything. And everything we do just about when it comes to signal processing, image processing, computing, everything like that is done in the digital domain, not in the continuous time domain. This is important because when I was growing up, when I was in college, the computers they would still teach you how to create an analog computer. Now, by analog, for instance, suppose you're solving differential equations. Do you remember with operational amplifiers, you could create a circuit that replicated a differential equation for any given input, and the output's voltage was the solution to the diff-EQ? I know you remember because you had me. That's an analog approach. We don't do that anymore. We only do digital because it's so much more efficient and there's so much less noise. And to be frank about it, there's no downside. Other than maybe you don't allow for an infinite number of possible values, right? Technically speaking, everything's quantized for digital processing. That's still nothing as far as a problem. So what I'm going to do, and there's like 2 or 3 things that are coming together right here, and this is important. And part of this, some of this isn't in Wentworth's book, but it's important you appreciate it. And I want to, because you're going to really see that this will be valuable for you later on. Really valuable. So what am I going to talk about? I'm going to say we're going to start with a periodic waveform that does this. Now, in truth, you all know that this is really something, they call it the PRI, pulse repetition interval and radar. And what I'm really trying to do is show you something that keeps on repeating itself. It's just a signal, it's repetitive. On this is going to be a digital signal. We might as well call this VFD because we're electrical and computer engineers. So it's a voltage versus time. This is 0. Now, this is termed usually the rise time. I know we'll get in arguments that, well, that's the rise time. If you were talking to Dr. New, he would say it'd be the time that it goes through 10% of its maximum value to 90%. There's differing opinions, but generally speaking, when we do analysis, radar work, electromagnetic compatibility, or electromagnetic interference, or any type of meaningful analysis for design, they just approximate this whole thing is a straight line. They call that T-rise, and they always make sure that that would be the worst case value, typically the longest value. Because you want a very fast rise time, usually. You want that thing to get right up to value and with no delays, because that way you can have smaller and smaller pulses and shorter duration time. This, and the way we do it is the length from this 50% point here, they call this tau, and tau is the on time, per se, on. And then the period T is here. They talk about something called the duty cycle, which is the percentage of the time the wave is high or on is tau over T. And tau, I'm going to refer to this as the on time. You may not see that in your textbook, but that's what it really is. It's the amount of time the thing is considered high or on. And that's a standard waveform that repeats itself, and we'll give it an amplitude of A, right? Now, that's a periodic pulse. And one thing you remember from signals and systems, if we're going to do frequency analysis and it's periodic, we use a Fourier series approximation. If it was not periodic, if it was just for a short interval, then we'd use Fourier transform analysis or Laplace transforms. Follow me on this? Because those are for things that have finite energy. If you have something that's repetitive or it's got an infinite energy, finite power, then you have to use Fourier series. Okay? So, now for the fun part. So what does this look like? Well, V of t, I'm going to use the exponential Fourier series, is equal to the summation of some C of n, e to the j n omega naught t, n goes from minus infinity to infinity. Most of you remember that, right? That's just the exponential Fourier series. When I have that, I can also say that C of n's value right here is actually found in a couple of ways. The most fundamental is 1 over the period, and I can prove this if you'd like. The integral from minus t over 2 to t over 2 times the function, in this case v of t, right? E to the minus j n omega naught t dt. And that's how you get the value of that constant. That's one way, right? Now, those of you who have had me, which is one person right now for signals and systems, this is the one thing that I really like doing to show you how to use, how to get a very quick approximation of that value by doing a derivative method. You all agree that I can take a derivative of this function. This is time. If I take a first derivative of this function, just get rid of that. That's the first derivative. What you can see is, well, this thing has a slope of a over tau rise. So it goes from 0 to a over tau rise. Then it goes back to 0 again, right? Then over here it goes negative. This would be tau rise. Matter of fact, I didn't put this down here, but this is tau fall. And they almost always make tau fall equal to tau rise. And whatever one is worse, they use. So normally, if you're looking at the bandwidth, they'll use the shortest if the shortest or the minimal value for the actual values of tau. Then if I come down here, at this point, we'll assume tau fall is tau rise right here. Then it goes negative. And the value here would be minus a over, we'll just call it tau rise here. And it will repeat itself, right? We'll just keep on repeating. As such, right? Well, just bear with me on this. This is still a periodic series, right? After I take a derivative, it's still periodic. Agreed, everyone? Mm-hmm. Because it's periodic, I can say, well, I have my v prime of t, that's the derivative, equal to the summation n equals minus infinity to infinity. This becomes, now I take a derivative of this with respect to time, or I get j and omega naught of prime times c of n times e to the j n omega naught t. Are you with me? Now, look, this right here is still a constant, right? That right there in purple, I can call it Cn prime. It's still a constant. It's equal to j n omega naught times the original value of Cn, right? And look, that's still a Fourier series, isn't it? A constant that is going to be a function of n times this. So that means this constant right here, right, still is related to that right there. Do you all agree with that? Mm-hmm. And I could go ahead and I could say that this constant right here would be equal to the integral of the derivative. Better yet, I can say that the C of n prime is still equal to 1 over t, the integral from minus t over 2 to t over 2 of, now it would be v prime of t times e to the minus j n omega naught t dt. And then one more derivative. Some of you know what I'm going to do with this. I'll put it, I'm going to put this right here. It's going to be a scale version. I like putting them right under each other. But then if I take a second derivative of v with respect to t squared, call it v double prime of t, and I plot that versus t, this is going to be the 0 point right here. Then take a look at this. Here it's important you pay attention. When I take a derivative of this, I get an impulse function. Do you all see that? All right, the impulse function is going to have a weight in front of it of a over tau rise. So this becomes a over tau rise, but it's an impulse. Then when I hit here, I had a negative impulse. This is going to be at tau rise. This will still have a value of minus A over tau rise. Then when I hit this point right here, it's going to have a value of minus A over tau rise again. And that point, believe it or not, is actually tau. And then when I come over here and hit this point, and that this is really gonna be tau plus tau rise, goes up to A over tau rise. And the whole thing repeats itself. And you all follow me on this? This is just one frame, one t, right? Now, the thing is, when I take another derivative of that, I get j and omega naught squared times c of n. You all see that? Take a derivative of this with respect to t, the j and omega naughts come out. So now I can say this series, and this is the important one. Let me erase this stuff. Now I can say that this series, v double prime of t, will be equal to the integral from minus t over 2 to t over 2 of 1 over t times v double prime of t e to the minus j n omega naught t dt. Sorry. This is going to be my c of n double prime. And I can say that my v double prime of t is equal to that Fourier series from n equals minus infinity to infinity of j n omega naught squared c of n times e to the j n omega naught t. And here we set this equal to c of n double prime, which is right here. Now I know it seems like we're just wasting a lot of time, but here's why. If I have an impulse function, I mean this right here is what the derivatives, the second derivatives I put in there, and then I do the integration, correct? Now take a look what happens. Let me just finish this train of thought here. Remember, I had the series of impulses, right? Now, when I go ahead and I say that my c of n double prime here is 1 over the period, integral from minus tau over 2 to tau over 2, double derivative of that thing. Well, there's just impulses. They all have a weight of a over tau. The first impulse is that t equals 0. I'm putting it in. The second impulse has a negative sign. This is going to be tau rise. Second impulse has a negative sense to it, and it's going to be at delta of t minus tau rise. The third impulse has got another negative sense. It's delta of t minus just tau. And the fourth impulse has got a positive sense, and it's t minus the quantity tau plus tau rise. Then, and I know I'm over, but I owe you time. Then, when all is said and done, this has to be multiplied by e to the minus j n omega naught t dt. Okay, now here's why I'm doing that. For a regular trapezoidal wave like this, it's really something that's got a rise time, fall time. To do the Fourier series coefficients with integrations, integration by parts, it's a pain in the butt. This is trivial. Why do you know it's trivial? Because when you have an impulse function, what is the integral of any impulse function, say t minus a times any function, f of t dt. If I go from minus infinity to infinity, do you remember how to do this? And in it, whenever I have an impulse function, the only value that's meaningful is when the argument goes to 0, right?
Mhm.
And when the argument goes to 0, the integration of an impulse function has a value of 1, right? But whatever value is next to it is turned on, and you pull out that value. So this integration results in simply f of a. Follow me? Because that's where this thing turns on at t equal a, right?
Mhm.
Is f of a. Now look here. This one turns on at t equals 0, correct?
Mhm.
Well, then I just evaluate what's next to it. That's a function of time. E to the 0 would be here, right? It's minus j and omega naught times t, but t would be 0, and that would be simply 1. Here, watch this. C of n double prime is equal to 1 over t. Now we're evaluating this integral, so it's going to have a coefficient of a over tau rise here. Then first one turns on, because it's an integration at 0, and it's just 1. Second one turns on at t is equal to t tau rise, right? With me?
Mhm.
Well, then you plug in tau rise here, and you get minus e to the minus j n omega naught tau rise. The next one turns on at tau. So it's minus e to the minus j n omega naught tau. And the final one turns on at tau plus tau rise. So that one's plus e to the minus j n omega naught tau plus tau rise. And I'll just tell you what I'm going to do. I know this is equal to C of n right there times j n omega naught squared, because I took two derivatives to get there. I'm going to give you some reading over the weekend, and therefore I can get C of n just by this divided by j n omega naught. Now, in truth, let me just finish my thought here. I'm going to take this crazy expression and turn it into something that makes sense. I'm going to turn it into a couple of signs, multiply it by each other, and divide it by some arguments that will eventually render them as just sinc functions. Remember good old sinc, sine of x over x, that are easy to understand? We're going to see that on Monday. And then I'll go through this. I'll give you some things to read this weekend. But the real reason I'm doing this is because this has so many applications. And if you see it here, you'll be very thankful you see it here and not have to strain later on figuring out what in the world's going on. But I'll take care of this with you on Monday, and you'll see this will start making sense. Okay? Now, I don't know, is the weather this weekend going to rain the whole time?